Thanks for the organizers for inviting me to give this talk. Um, so I should mention that my background is mainly in collider physics, and it's the upcoming uh, electron-ion collider experiment that's basically got me interested into this physics of the hadron structure. Um, and today I'm going to present some work I did in the past 6 months or so with my collaborator Puya Asadi, who is currently a postdoc at the University of Oregon. Um, and as the title suggests, the basic premise of the talk is that um, we want to understand whether it's possible to uncover the structure of the hadron, um, appealing to some organizational principle that's based on the entanglement properties of the partons that make up the hadrons. So that's going to be the main premise of the talk. So let's get started. So from an experimental point of view, most of our information about the structure of the hadron comes from scattering experiments. And the quintessential experiment for that is the deep inelastic scattering one, in which I have a highly virtual photon, which is probing the microscopic physics of my hadron. So in this process, I have two scales, which are essentially the photon momentum q and the hadron mass, lambda QCD. And if I have a large enough separation between these two scales, then I can write down a factorization equation which neatly separates out the perturbative physics, which sits at the scale q and is process dependent, which in this case depends on what I measure on the final state. And it neatly separates this out from the universal but process independent physics, which is just the non-perturbative structure functions, which we're all familiar with, which in this case is the parton distribution function, and we can have generalizations of those. And this is correct to leading order in the expansion parameter of my effective field theory in some sense, which is lambda QCD over Q in this case. So this object here, which is the PDF in this case, I'm sure all of you are familiar with it, is just the projection of the hadronic state onto a bilinear operator, which is separated on the light cone. And it has a very simple physical interpretation that we can interpret that it's a function of this variable x, and we can interpret that as the number density of partons of that particular species. So in this case, it's a quark carrying a fraction x of the boosted hadron momentum. So that's kind of the simple interpretation of this object. And the question we want to ask is, can we use ideas from quantum information in order to get an analytical handle on the computing this object? So that's going to be the concrete question that we want to ask here. All right. So obviously, computing the PDF from first principle is kind of intractable, mostly because I don't have an expansion parameter in the IR. Neither is there any dual theory which I can appeal to do a weak coupling calculation. So in that respect, really lattice is the only tool I have, but unfortunately, because of the fact that I want to compute this object which is separated on the light cone and is not spatially separated, I can't directly compute it on the lattice. And the only thing we can do so far are moments of the PDF in some sense. Although there have been some really ingenious techniques in the recent years that allow us to compute the PDF, at least in some regime of this Bjorken X, by mapping them onto space-like correlators. But I won't talk about that here. So because of this, most of the community then turned towards looking at some simpler models in lower dimensions that exhibit behavior like QCD. So this was mainly so that you can strip away some complications and uncover some basic physics. And also mainly because the simplification that ensued allowed us to solve these theories in certain limits, either analytically or numerically. Of course, these were solvable because they relied on certain specific properties of those theories, such as the existence of a duality or some special symmetries of the theory, or even numerical calculations. But as far as I know, any of these techniques are specialized to those specific theories, and so far we have been unable to apply them directly to QCD in any simple manner. So the point of view that we wanted to take is we do want to look again at these theories, but with the point of view that instead of looking or focusing on the specific properties of these theories, that make them solvable. Instead, we want to sort of see whether we can extract some general principle which is obeyed by all of these theories, specifically focusing on, as I said, the quantum entanglement properties of the partons that make up the bound states in these theories. So we do not want to rely on the special properties of these theories, specifically because we want to apply them eventually to higher dimensions, where we don't have these luxuries. So that's what we're going to do. And obviously, working our way up from lower dimensions allows us to add layers of complications systematically. And so it allows us to isolate certain complications one at a time and study them. So that's going to be the general idea. Okay, so we'll start with gauge theories in 1+1D. I'm sure everybody is familiar with this. I'll just give you a quick primer and highlight the main properties that will be useful for understanding the analysis further on. So first of all, the gauge coupling is dimensionful, and it plays the role of lambda QCD in 1+1D. And so the strength of the interaction between the partons is really controlled by the ratio of the gauge coupling and the quark mass, in this case, MQ. Once I fix the gauge field is no longer a propagating degree of freedom, but it does show its presence by the presence of a confining potential between the charge densities, in this case, the fermions. Since ultimately I want to compute the parton distribution functions, in this case, we have a great simplification because of the fact that the coupling is dimensionful. All the radiative corrections of that PDF are going to be power suppressed by the scale G over Q. Okay, so essentially what that means is that I can compute that operator that I was talking about, the PDF, at tree level in 1+1D and ignore all radiative corrections. And so the problem essentially reduces to the description of the bound state in the partonic basis. Okay. So the theory that I'm going to be considering is the most basic one, the Schwinger model and Hooft model in 1+1D, which is respectively QED and QCD in that dimension. And since I want to compute the PDF, which is most easily defined in a boosted frame of the hadron, that's why I'm going to use the Hamiltonian in the light cone gauge and use light front quantization techniques, where x plus will be my time variable and correspondingly p minus will be the Hamiltonian. So in both cases, the Hamiltonian looks pretty simple. I have a kinetic term, which is proportional to the mass square, and I have an interaction term, and that's about it. And the interaction term is basically a long-range linearly confining potential between two charges, two charge densities, which is instantaneous in time. And this form of the potential is pretty interesting because this is the one which also shows up consistently in higher dimensions all the way up. All we do is stack on more and more integrals over the other dimensions, but otherwise the potential form of the potential actually remains the same. And that's true in both of these theories. Now, in case of the Schwinger model, this actually is solved in 1+1D either by bosonization in the large coupling limit or in the intermediate couplings. You have to do some numerical techniques, either lattice or the discrete light cone quantization, which was implemented by, I think, Stan and his collaborators, as well as Wilson to some extent. On the other hand, for the Hooft model, the spectrum is solved by, obviously, Hooft equation at large n, whereas the baryon and the meson at finite n, again, can be solved using discrete light cone quantization. So what is remarkable in 1+1D is if I use light cone quantization, then what happens is that the ground state or low-lying bound states of the theory are very easily describable in terms of the Fock space of only valence partons, which means that the higher contributions from the higher Fock space, at least for the low-lying states, are heavily suppressed, which makes our analysis extremely simple in 1+1D. Okay. So that's sort of a background. And so let's look at essentially what the spectrum looks like. So for the Schwinger, obviously it's a gap, the spectrum is gapped even at 0 quark mass. And as I increase the quark mass or equivalently reduce the strength of reduce the strength of the coupling, the mass increases more or less linearly. So that side essentially is the small coupling or infinite mass limit, and this is the mass of the hadron, which is the meson, in terms of the gauge coupling. Okay. For the fifth model, the situation is slightly different. We don't have a gap. Both the baryon and the meson have zero mass at zero quark mass, but the behavior higher masses is similar to the case of the Schwinger model in that case, in that sense that it monotonically increases as the coupling becomes weaker and weaker. So just looking at the spectrum, it doesn't really tell you much about what's going on internally. But what we can do is we can look at the parton distribution functions for the quark and the anti-quark, which are the same in this case because of the symmetry, in both of these theories. Yeah, DLQC. Yeah. So there is a it's truncating to two body using the QQ bar state. Yeah, and solving the Schrodinger equation in the large n limit, or by using the DLQC technique by Stan or Hornbostel. You can include higher components. So as far as I know, for the lightest bound state, so this is the ground state meson. For the higher bound states, it becomes important if I go to really high n or excited states. For the ground states and lighter state, the contribution from the higher Fock states is really suppressed. So that's why.
You want to really determine the precise mass
you mean with the but this is not this, these are all ground states, right? I'm not going to excited states at all. Right now, probably I can get away with just the, but yeah, I'm going to stick to QQ bar for the valence quark description for now. With higher Fock states?
I don't remember. I think he was doing not this, but
I see. No, I haven't probably seen his paper. Yeah. So we were looking specifically for the papers which gave me the parton distribution function, and there aren't. You have that as well? Okay. Yeah, I'll be happy to take a look as to what. Okay. Yeah. Yeah. Data of the points. I'll show you the curves are our predictions, but I'll come to that later. But I'll talk about that later. So yeah, but the point is that what I wanted to take a look at was the parton distribution functions in these two theories. Specifically, if I look at the meson parton distribution function for the quark and the anti-quark, for both of these theories, then what I see is that in the limit that the coupling goes to infinity or the quark mass goes to 0, the PDF is actually really simple. It's just 1. That's all it is. So it's uniform, and this is basically the PDF plotted as a function of x, which is the momentum fraction of the hadron. Okay, so that's all it is. On the other hand, when I go to the weak coupling limit, where MQ goes to infinity, basically the PDF approaches a Dirac delta, which is centered at half, essentially. So you have two free quarks, or a free quark and anti-quark, each carrying 1/2 of the fraction of the hadron momentum, and that's all you have. Okay, that's a pretty simple picture, and this holds for both of these theories for the meson. Okay, so in that sense, irrespective of what the spectrum might look like, we have some sort of universality of behavior for the parton distribution function, at least across theories. And from this picture, what we can infer is that because of the fact that the PDF is just a constant or 1, what this means essentially is that if I express the bound state in momentum basis, then it is maximally entangled. Okay, the quark and the anti-quark are essentially maximally entangled in this limit. Whereas here, when the approach is a Dirac delta, they're essentially unentangled. Okay, and that's in momentum space. So the system is basically going from a maximally entangled state to a disentangled state as I dial the coupling from infinity to 0. Okay, so that's the simple picture that emerges here. And that basically prompts us to say something like this. It seems to be that the system is actually organizing itself on some coupling dependent strength measure based on some coupling dependent strength measure of quantum entanglement. So that's what we want to say. And I'll talk about that for the rest of the talk. Okay. Okay. Any questions so far? All right. Okay. So what should this principle look like? We already have some clue about what it should look like. Yeah. Just on the basis, yeah, for now. Yeah. All right. So what should the principle look like? So we have some clue as to what it should be. We know that at least in the maximum or in the infinite coupling limit, it should be maximally entangled. And so at least in that regime, we can make a simple guess, which is to say, let's just see whether or not some kind of an entropy measure or entangled entropy measure would work as kind of a organizational principle for this bound state structure. Okay, so the simplest thing I can actually guess at is just the 1 Neumann entanglement entropy, which is defined here. And I know that in the limit where the coupling goes to infinity, I'm going to extremize S, and that will be my maximum entropy principle in that regime. But I also want to describe the system as it moves away systematically from G is equal to infinity. And in that regime, the only other object that's available to me, if once I looking at the Hamiltonian, is the kinetic term. And so we could possibly make an analogy with thermodynamics, although a hand wavy one, in which given that we are using some entropy measure for in the maximum in the infinite coupling limit, we can conjecture that moving away from this infinite coupling limit could be achieved by minimizing some kind of a free energy, where this E should be proportional to m square, because that's what we'll get away from the m is equal to 0 limit systematically. And the only term that's available to me is the kinetic energy here. So in this particular case for the meson, it's you are tracing over one of the antiquarks and you're computing the entanglement entropy between the quark and the antiquark essentially in this case. Yeah. So that's what we want to what we'll put here and see what happens. Okay, as an ansatz for this free energy. Okay, so here's how it will work. Essentially, if I start off with a meson wave function, well, I'm writing it on a discrete basis, but that's just for normalization. I can easily take the continuum limit. So P here is just the wave function, and it's written in terms of I and J bar, which are the x basically, which are the fraction of the momenta carried by the quark and the antiquark respectively. And so this is the eigenstate of P plus operator. And what we can do is, as I said, we can trace over the quark or the antiquark and get a reduced density matrix. And because of this specific form, as it turns out, the density matrix is actually diagonal because of the fact that the momenta add up to 1. That constraint basically makes it diagonal. Thanks. And so it's pretty easy to compute the entanglement entropy in this case. And subsequently, the kinetic energy is just the term proportional to P square, assuming this form of the wave function. And minimizing this free energy essentially gives us an ansatz which looks like a thermal ansatz, not surprisingly, because we use a free energy ansatz as our input. So basically what the wave function looks like is something like this. As a fraction x and 1 minus x, it's basically given as e to the power 1 over t times the kinetic energy, which just follows from our conjecture of it being a free energy. Now what we're going to do is plug this in into our Hamiltonian and minimize the expectation value of our Hamiltonian with t as the variational parameter. Okay. And what this will allow me to do is to calculate both the value of the T, the bound state mass, and fixing those will basically also give me the parton distribution function. Okay, that's the idea. All right, so let's see how accurate is a thermal description. As it turns out, it's pretty damn accurate, at least over a large range of couplings. If you see this, so the blue line is basically our estimate for what this spectrum looks like, and the golden line is the numerical result that I showed you earlier. As you can see, in the large mass limit, which is the weak coupling limit, the correspondence seems to be exact. And as I move towards more and more towards the non-perturbative regime, there is a systematic deviation from thermal behavior. And we can see that even if we compare what the parton distribution functions look like. So this is, for example, for a large ratio of MQ to G, I almost have a perfect agreement with what the PDF should look like. Whereas when I move away from it, I see systematic deviations. Okay, so that's kind of the behavior that we see when we introduce these thermal ansatz. And the same thing seems to be true for the Thuft ansatz as well, for the Thuft model as well. So in this case also, I'm just showing the meson. I'll come to the baryon momentarily. So even in this case, I see the same behavior, but it's remarkable that even at order 1 couplings, we still get a pretty good description of the system just using a thermal ansatz. Okay. However, the thermal description does not work in the deep non-perturbative regime, but looks exact as at infinite mass. And so we want to ask the question, can we do any better than this? Okay, so the obvious thing to do, as of now, no. Yeah, so I have no idea as of now. I can only say that it should go from this maximally entangled to the free theory. So in that sense, it makes sense. But I have no direct intuition as to why it should be that way. Yeah, but yeah, I'm open to suggestions. Okay, so we wanted to see whether we could do any better. Obviously, our guess at a thermal description seems to work somewhat, but not too good, not too well. And so what we decided that maybe we could generalize our entanglement measure. And the most obvious generalization we could think of was just the what is known as the Rényi entropy, which is a natural generalization of the von Neumann entropy, and which is a function of this parameter alpha, which is we can think of it as the order of the entropy, and reduces to the von Neumann entropy in the limit alpha going to 1. Okay. So that prompts us to change our ansatz and use this generalization, and hoping that in the weak coupling limit, alpha should go to 1, and therefore we should get our thermal result back in the limit as the coupling becomes small. Now, if you plug that in and follow the same steps, our exponential ansatz now turns into something which looks more like a power law. And if you see this behavior, this is very reminiscent of what the PDFs look like in 3+1D. For those who might be familiar with the fitting of PDFs from data in 3+1D. So what we have done is we have replaced T with a different variational parameter, which is alpha, which in this case is the order of the Rényi entropy. All right. So let's see how well does this do. Yeah. You do, but the T is basically fixed by normalization. I don't have to obtain it by the minimization of the Hamiltonian. So it's just fixed by the fact that the probability should add up to 1. That's all. Yeah. So it's not a different parameter. It was a variational parameter before. Why is it different? Oh, because if you look, so the T is buried in this N basically.
Why wasn't it buried in the N?
Oh, because it was in the exponent, right?
Oh, I see.
Yeah.
That's
Because of the form of the exponent. Yeah. All right. So let's see how well does this do. It seems to do pretty well in the sense that I really, from looking at it just by eye, I cannot really tell the difference between the numerical result and this ansatz. So first of all, it does give me a pretty accurate description of the spectrum all the way down to zero mass, which is in the non-perturbative regime, both for the case of the Schwinger model as a 't Hooft model. And the PDFs also look, at least compared with whatever data we have available, I do seem to have a very good agreement with all the numerical results as well. What is peculiar is that if I now plot my variational parameter as a function of the coupling, then as expected in the large mass limit, it's going to 1. So I'm recovering a thermal description in the large mass limit. But what you see here is as I enter the non-perturbative regime, alpha becomes negative. And that is really something peculiar because Renier entropy is usually defined only for positive alpha. And what we think statistically is happening is that, so the normalization parameter T also switches sign with alpha. And what the system appears to be doing then in this case is that it's switching basically from maximizing the high probability configurations to minimizing the low probability ones as I go from positive to negative alpha. No, it's a combination with the free energy, right? It's part of the it's the kinetic energy minus the it's a free energy part. Yeah.
Right. But you're computing that. So, but this is n that satisfies the square law test.
Yes. Yeah. And this alpha is just the order of the entropy as a function of the yeah. Yeah, I'll come to the baryon case. Yeah. This is just for the meson. For the baryon, it works slightly differently. And since I have a few minutes left,
Right.
yeah, they are pretty close to each other. Yes. I mean, for now, I just know that that is numerically, that's what it's giving me, that for both the mesons and the baryons, it's giving me the same, more or less the same value of alpha, which is interesting. Yeah. No, so this will only work for the ground state, because if you see in the excited states of, for example, in the Schwinger model, they have you have more and more kinks, right? As I go to excited states in the PDF. And so I don't think it actually follows a minimization principle of this sort as I go to excited states. So it actually doesn't work as far as I know. All right. So for the baryon case, the analysis is slightly different. So if I start again with a valence quark state, a 3-quark state, and write, so ignoring color indices for now, just write it as a wave function in terms of ijk, which are again the momentum fraction of the hadron momentum. Then if I trace over one of the quarks, say the quark momentum k, then what I can do is I can write the density matrix as a weighted sum over 2 quark pure density matrices. Okay, so this is a weight factor, and once I trace over the quark with the momentum k, I can rewrite it in terms of a weighted sum over pure density matrices. Okay, and why we do that is ultimately what we're doing is, instead of tracing out both quarks and then minimizing the or maximizing the entropy of the reduced density matrix of a single quark, what we are doing is we are applying a minimum free energy principle for each biquark system or biparton system in this case. Okay, and the reason for that is I think dictated by the form of the interaction Hamiltonian, which is to say that the Hamiltonian basically is of the form of a 2-to-2 charge interaction, which is long distance of localized charges, which is why we are saying that that is the correct way to actually apply this minimization principle. Okay, and I can talk more about this. And that's the answers that we get. And so if I now look at the baryon mass, I still get a pretty good description of the mass spectrum, although the data in this lower mass limit is not very reliable from numerical techniques, so I don't have too many data points there. Unfortunately, so we can test the PDF as well for zero mass. At zero mass, it's basically a straight line which goes like that, so we recover that. But for the rest of the masses, again, we do not have any reliable PDF data. So as far as I know, Stan's paper has some of these plots, but there are some numerical issues with those. So we weren't entirely sure whether to compare with them or not for now. But if any of you know any other sources of PDFs for the baryons, just for the baryons in 1+1D, it would be very helpful for doing this comparison. Yes, Hornbostel's, okay, thesis, okay, not the paper you're saying. Well, okay, I'll take a look. I mean, the general shape is correct, but we wanted to see whether we can get a complete agreement with the numbers. Okay, so in the couple of minutes, maybe I can talk about how would you possibly apply any of these ideas to higher dimensions, which is very much a work in progress. And I would love to have input from guys here who are probably far more experienced in this field than I am. So what we decided to look at was 2+1D Yang-Mills, simply because it had only a single degree of freedom and a single scale once I fix the gauge. So that makes it, at least in terms of the number of degrees of freedom, it's pretty small. But again, the gauge coupling is the only scale in the problem, which now scales as m to the power half. But the running of the PDF operator is still suppressed. So as you can see, the interaction piece looks pretty much like the one in 1+1D, in the sense that I have an instantaneous gluon potential between charge densities. But I also have a 3 gluon term here, which will now enable splitting of gluons into multiple gluons. So, but for now, the only point I want to get across is that G square over PT, because there is no mass here, G square over PT actually plays the role of the dimensionless measure of the interaction strength. And so from here, it's trivially clear that there is a symptotic freedom in this theory in that sense. So we're going to stick to our description in terms of valence patterns for now, and just as a test case. And starting off with the lowest ground state, which is the glue ball with zero angular momentum and CP even state. We can construct some state with an unknown wave function shy of p per comma x for which we want to apply our free energy ansatz again. And finally, so what I want to point out is, if I look at the kinetic energy, which is one part of our free energy ansatz, and compare it with the 1+1D, the difference is that the place of m square now is being basically taken by PT square in this case. Okay, because that's what we are doing. We're integrating over all PT. So in some sense, what we are doing is we are integrating over all coupling strengths, right? Once we are integrating over PT. So which means that the plot that I showed you, in which alpha varies as a function of m, I have to integrate over that entire plot to get a single mass spectrum for bound state for this one, because of the fact that the coupling strength is varying with PT. Okay, so that's the idea. So that's what we are doing. Effectively, we are summing over configurations over all possible mass couplings. And if we take that lesson from 1+1D, then it's natural that the order of the Renyi entropy must now become a function of PT, because that's what the 1+1D is telling me. And so what we are doing is that we're extremizing the free energy for every slice of PT, essentially, okay, based on this intuition. And that gives us, again, a very simple ansatz. I'll not go into details, but I'll be happy to discuss how we derive this. And this is essentially some form of a TMD PDF for those who are familiar with this, which is the transverse momentum dependent photon distribution function. Okay, I think I'll stop in a minute. I'll not go through the technicalities. I spent the last 1 month trying to understand how to get a finite Hamiltonian expectation value, because there are well, IR divergences are easy to handle, but there are some spurious divergences from the zero mode that appear in light front quantization. But I think there's a good explanation of how to handle them in Wilson's paper. So that's what my attention has been for the past month or so. So unfortunately, I don't have the numerical results here, but what we're going to do is essentially treat the Hamiltonian as a functional of this alpha of PT, and that will give us an integral equation for alpha of PT in this case, because I am integrating over all slices of PT essentially. All right. Okay, I'll stop here with the outlook. So essentially, obviously, I haven't answered some of the interesting questions like, will this entropy ansatz actually capture the linear confinement that we see in 2+1D, which is actually not visible perturbatively, right? So that's the big question. Obviously, I have ignored any higher Fock space contributions, and even though it appears that when I look in the light cone light front quantization, at least in 1+1D, I see that I can give a very good description based on just the valence partons, but I have yet no intuition as to when these C partons or higher Fock states become important and how to include them systematically. And once we do include them, how do I change my free energy principle, because I no longer have a definite number of particles to play with. So that would be obviously, once we go to 3+1D, you have radiative corrections to deal with for the PDF operator as well, which may or may not be perturbative always. So, all right, thank you.
So, we talked about this alpha. So, if you get say signature to the hardware
Mhm.
then you can basically see it as a variation and that, and the solution all have the boundary condition that basically goes like x times 1 minus x
Yes.
alpha.
Yeah. Near the boundary, it does go like that. Yes. Yeah.
So maybe like one conjecture is that the linear entropy and that works so well because it captures the spread boundary to alpha spread.
Right.
Then if you use sort of non-entropy,
Yes. Yeah, that's true. So yeah.
So one idea that was suggested rather than the radiant alpha using the model solace.
Yes, we have. It gives the same ansatz for us. Yeah, either one is useful. We can use either one. It gives me the same x1 minus x to the power alpha law. Yeah.
Yeah, so it's not here 0.2 in the characteristic time scale which tells you when high point states stuff.
Right. Right. So
sorry. Yeah, I wouldn't expect that small x to be that correct because I would expect more.
yes. So if I look at 3.1+1B PDF, that's what I see, that the baryon PDF that I show has a similar shape in 3+1D, but it shoots up as I go to low x, and those mainly come from small x contributions from the radiative corrections. So that seems to indicate that most of the radiative corrections are going to come in that regime. And so maybe I can appeal to some effective theories like SCET perhaps, which are designed to work in certain specific kinematic regimes to capture those radiative corrections. Yeah, so that might be.
Last question.
Yeah. Right. Yeah. In the large mass limit, it becomes a perturbative theory essentially. So you can solve it. Yeah. And sorry, can you repeat that? Yes. Yes, they do. I mean, numerically they do, right? So, I mean, I haven't checked analytically the same expression. Yeah. So yeah, that would be an interesting check to do.
Okay, let's take the root again.